then. Okay, so next talk is by Paolo Carios from the Institut de Mathématiques de Toulouse. Paulo will talk about cyclic cohomology and the topological K-theory for discrete groups.
Thank you very much, Katia, and thank you very much for the opportunity to speak here. It's really an honor to be right now speaking at this conference. I would prefer to be in Toronto, but okay, it's very nice already. So yeah, I'm going to talk about this this work in collaboration with Bailing Wang and Han Wang that follows a little bit the discussions that we're having, Alain and Paolo and Yuliang, and based on the talk of John. But with a more geometric approach. So essentially, my goal here is to tell you how to, well, a possible way to, well, not a way, but I mean, I will tell you how to pair the left-hand side of Baum-Connes assembly map with cyclic periodic cohomology of the group algebra and sketch the proof of possible index formula as was asked by Alan some minutes ago. But as usual in my talks, well, at this talk, I'm sorry, this talk I gave it in the global non-commutative seminar, so it's just the first part. The second part, in fact, is new. So sorry for those that were there. So I always start with this Atiyah Singer because it's how I understand the assembly maps. Following Atiyah Singer and Connes-Candalis and Baum-Connes. So I will start with a closed smooth manifold just to recall you what Atiyah Singer do. So they have an elliptic operator, so the differential, let's say, acting on, and you can associate it the index. So this map is in fact, well, it goes to the integrals because the index is the dimension of the kernel minus the dimension of the co-kernel. But in fact, well, for me, the main contribution of Atiyah Singer is to put K-theory into the game once you want to compute these things. So the first thing is that in fact, the elliptic. Sorry, there's a question. No, I heard something. Sorry.
Ladies and gentlemen, the weekend.
Is that okay?
I think we might have some intruder. But
Yeah, yeah.
It will be stopped.
No problem. Okay, I was saying, well, this is Atiyah Singer, well, just the index map, sorry, the index association. And then Atiyah and Singer, well, they realized using the previous work of Atiyah, and here's the question: there's a good quotient for the set of elliptic operators, which is in fact the topological K-theory of the cotangent bundle. And by good quotient, I mean that, well, there's a map which is the principal symbol class, which is surjective, and in fact that this map passes to the quotient, so it factors. But now, in fact, this map that I denoted index. Sorry, let me take back my cursor. So this one is not just a map; it's in fact a morphism between groups, and K-theoretical groups, because the integrals here is looked as the K-theory for point. And this once you are in K-theory, you can use all the cohomological properties of K-theory, and this is what Atiyah Singer did for compute index formulas. But well, in particular, to go into the subject of my talk, let me just tell you that if M is a spin C, let's say, just to try to illustrate my point and get to Baum-Connes assembly maps, then well, you have a Thom isomorphism from the K-theory of M. And then, in fact, well, this map, which is the composition, you can well see by Poincaré duality that in fact corresponds really to the projection, to the push forward associated to the projection to a point. So usually K-theory is a contravariant functor, but using index theory, in fact, you can dualize it to define push forwards. So why I'm saying this? Because, well, how to get index theorems, computing indices. Well, I will say it in not exactly as Atiyah Singer, but more in the Connes-Candalis way, is that once you give a sense to the push forward functoriality, so that means it's a ground wave functoriality because it's, if you have a map from M to M prime, then usually in topological K-theory, you have a pullback. And But once you give a sense that I will, in fact, later on tell you how to give a sense geometrically, even in the equivariant case, for appropriate F, so K-oriented and with good conditions in K-theory, then, in fact, the index theorem can be obtained from push-forward functoriality. In fact, this is what Atiyah Singer did for a particular case of push-forward by embedding the compact manifold in some Rn and using some normal bundle, and but essentially the axioms that they give they are equivalent to the push-forward functoriality in this case. So this is what I say. So in fact, the topological index theorem, well, is equivalent to the push-forward functoriality, so meaning that these kind of diagrams commute. And the topological index formula so is obtained by comparing the strict maps with their cohomological versions. So this is kind of Riemann-Roch theorem. In the case of Atiyah Singer, you only need to understand how to compare the Thom isomorphism in K-theory and in cohomology via the Chern character. And there's where the thought classes appear and so on. This will appear later also in my talk. So, okay, but in fact, once you put in terms of freak maps, then you can replace, I mean, this has been done, it was already done by Atiyah and Singer in the family case. So you can, instead of working with a point, you can take a manifold that live over B. Because essentially what I want to point out is that here you are obtaining the K-theory point as assembling the different manifolds that project to the point, which are every manifold in this case, of course. But if you change now by another base, let's say B, then the same, in fact, this is a copy-paste thing once you are doing push-forward functoriality. So once you give a sense to strict map, you can prove a family index theorem as Atiyah Singer. You can prove it using just the push-forward functoriality. So this means, again, that this kind of diagrams commute. Sorry, I didn't change the name pi m. Well, in this case, pi m is not a point, but just to be. And again, you can obtain the index formulas by comparing again with cohomology, with the strict maps, that in this case you can do by classic methods because you don't have groups or something different. Now, in non-commutative geometry, for example, in the pioneer work by Connes and Scandalis, you can allow more interesting spaces than just B. For example, B can be replaced by some space of leaves with a regular relation. This was one of the works that motivated this story for me. And then, okay, but you can also replace it by a group. But of course, in this talk, well, I will replace it by a discrete group. But of course, now you don't take just the K-theory, topological K-theory of the topological space gamma, because this is not good. But well, you can use sister algebras, for example. So now I will come to Baum-Connes assembly map as I understood this thing in the original papers of Baum-Connes. Well, original, I mean the first ones, because then afterwards the KK theory came into the game and other models as I will try to sketch. But the point is in some way the same idea, but you have a manifold which now comes equipped with an action, it's a proper action by gamma, as you say, let's say spin C, co-compact maybe for the, not now, but later on will be necessarily. So in fact, you can, Baum-Connes were originally interested in higher index maps. So this I will in fact recall the geometric definition of these maps. But essentially, these are higher indices, as have been mentioned in several talks during the week. And they were interested in this to obtain higher index formulas, as also we have heard a lot of this in these weeks, but also for applications, of course, as the homotop invariance of higher signatures is perhaps the most famous one that has been mentioned also several times during the week. So how to assemble these things? So following the motivation I tried to sketch in the previous slides. Well, in fact, Baum-Connes, they assembled, they put together all the manifolds that that go to a point and that have proper actions, and they wanted first that to have this kind of diagrams. So push forward functoriality to get an assembly map where by definition here this is just the limit. So in fact, if you have the push forward functoriality, you have this group. Well, this group by definition the limit. Okay, and then the assembly map is just defined by taking a manifold like that, an element in K-theory, in equivariant K-theory. Sorry, I forgot to mention that here. For me, this is just a K-theory. Well, the K-theory of the C-star algebra of a groupoid, of an action groupoid. So this is a proper action, so it can admit another more geometric models as well. So the assembly map is just taking this Schrick map. But in fact, okay, so in fact, well, as also we have heard a lot about it, a very interesting conjecture because of the geometrical consequences it implies. So they Baum-Connes, they conjecture that this mu, this assembly map is an isomorphism, and this is still open. It's still an open problem. And in the importance of this is because it has many consequences and of different nature, topological nature, geometrical nature, analytic nature. And okay, but in order to have the above assembly map, the one I was describing with push forwards, well, first you need to define the push forward. And then, well, you have to prove the functoriality, because otherwise you don't have the commutative diagrams I was mentioning that define the group. So this is what I say, the group is well defined only if this version of the group is well defined only if you have the functoriality. And the assembly map in that case is also well defined if you're allowed to have Schrick maps to a point. And well, in the original papers, Paul and Alain Cohn, this was only a sketch with a lot of the main ideas that gave birth to this very interesting and wide research domain. But they gave the ideas, but then some years after they formalized these ideas with a powerful tool that was K-theory. Together with Higgs, and they given a different model, which is called by some people the analytic version of the left-hand side. And then they defined the assembly map, and well, from then a lot of results were obtained using this model for different kind of groups. And through the years, other models were proposed for the left-hand side. There's the famous Baum-Douglas model, which is of more geometric nature, and there are different models, for example, proposed by Luke, using more topological techniques. So, well, but what about the original model? Well, this is what I was interested in from some years now. The original model was supposed to be very geometric. And in fact, this is what I will tell you about in the first part of the talk. And eventually we'll get to cyclic cohomology and homology. So some years ago with Bai-Ling Wang, we used deformation groupoids. And as I will explain in some slides, there's a very geometric definition for this push forwards using groupoids. So I really to emphasize, and I will say it several times maybe, that in principle we are talking about a discrete group, but groupoids will appear everywhere, not just because the gamma is a group, because in these constructions of indices they will play a very important role. They are always there, even if you don't use it explicitly. But I will use it explicitly, the notion of groupoids, and particular groupoids, which are very useful in this case, as I will try to tell you. So, well, we did this. I will recall it briefly because I will say a word that how to adapt this in cohomology, and we proved that the one-way functoriality, well, in a lighter general case, twisted groupoids, and we obtained this that at least the map was the group was well defined and the assembly was well defined. But then, well, for me, at least, the importance of the original model is that it was, for me, the ideas were really to compute explicit higher index formulas. That was asking some minutes ago, Alain, to how to compute explicit formulas. This is somehow hard because, well, the other models, you need sometimes analytic conditions or other kind of conditions, or in the topological model, sometimes you don't have the explicit cycles. So every model has, of course, its advantages. So I will try to sketch the construction of push forwards and the result that it will be to transform this to cyclic cohomology. So I need to explain you geometrically how these maps are defined. And I need to do a digression on deformation to the normal cone and push forwards. So this is a very geometric construction, which I have been using since always. I started my thesis. It's a very, you can put it really as an exercise to your third year students. I have done it, so this is what I'm sure. So you take a manifold in a manifold, so X in M, and in fact you can well define the set. The set is just a set where n is just the normal bundle, so it's okay. And in fact, you can put in a C-infinity structure in it, such that it's a nice one. So such that this part is still open with its canonical product structure. It's an open dense part, and this one is closed, of course, but with its canonical structure given by the structure of the tangent space. So this is well, it's just a construction, but it appears a lot in differential geometry, in algebraic, the analog one in algebraic geometry as well, very related to blow-ups and so on. But well, the main feature is that in fact it has good functoriality properties. So I mean that if you have a map from couples, I mean that you have a map from M to M prime, and it sends X to X prime. So in fact you have a map, a C-infinity map. This is where I mean you can put it as an exercise in the differential geometry literature. The map, well, I have to tell you what the map is. The map is just F, essentially, with UR for epsilon different from 0, and in 0 is just the differential in the normal direction. So you have a normal vector, then because F sends X to X prime, then the differential passes to the quotient, to the normal bundles, and it's functorial. So okay, functorial is a big word for undergraduate students maybe, but well, you have the classic properties of functoriality. It respects everything, compositions and so on. But this is okay, just an exercise, but it has deep consequences in groupoid theory, for example, because if you have a groupoid inclusion, so one groupoid in another one, then you can explode this inclusion. So by applying the differential to the normal cone construction to the entire inclusion. So all the maps, the structural maps are going to be deformations. And this is just a corollary, but it's a big word. You know, you obtain a Lie groupoid. So you not just a set theoretical groupoid, but it's a Lie groupoid. It has all the structure is compatible with the deformations. So the main example for this is Kohn tangent groupoid, which is just the inclusion of M in M times M as the diagonal. So the first one is a groupoid, which is just M over M, and the second one is just the pair groupoid. And this was a very nice feature, geometric object that, for example, Kohn used to describe the geometrical way to prove Atiyah Singer precisely in his book, and then has been used by several people. And I will use this construction because, well, I will say a word. Well, I will recall the push forward in equivariant K-theory, but first I will do it without equivariant, and then I will say how it adapts to equivariant. So you take a map from M to N, C-infinity between two manifolds, and you change this map by this one. Just take a F and take the diagonal. But it's not just a map between manifolds now anymore. It's a groupoid immersion, because here m times m is not the manifold m times m, is the pair groupoid. And this is extremely important, because in fact for me I mean, these two maps are in fact the same from the stack point of view. You know, m times m is Morita equivalent to a point from the groupoid point of view. So in fact, this is the same map. Well, in some word, it is the same map. But if you apply this construction that I was mentioning, the deformation to the normal cone, and you obtain a Lie groupoid applied to this map. In fact, it's explicitly described here. So here is an identification of the normal bundle of this in this, of m in n times m, the pair groupoid. And in fact, well, it's a Lie groupoid. So for Lie groupoids, there are, well, sister algebras. And in this particular case of this groupoid is in fact a family of groupoids over well, I just put it in over this closed interval because it's important for the what follows. Originally it was over R star, but I can restrict to just the closed interval 0, 1. So in fact, the main point is that there are short exact sequences. In particular, well, here you have just evaluation at 0, which gives the algebra in the 0 part. And then in sister algebra, you can show that the kernel is in fact what is missing in the other side. So what you see geometrically, you see it in the short exact sequence. But it's a short exact sequence. This has been shown by several people, Jean Renaud in more general context, in Hilsum Scandalis, and also in their paper on wrong-way functoriality. In even more general cases can be shown. But the point is that if you have a, well, this is it's not just a short sequence, but this is in fact, in this particular case, this algebra here in the kernel is contractible. So if you apply a functor, which is homotopy invariant and has long exact sequences, or in particular a six-term exact sequence as K-theory, in fact, you get that this map will induce in K-theory an isomorphism. Because this algebra here will be contractible. And this is contractible by trivial reasons, because the presence of this open closed interval. So once you have that, in fact, you can define now the family index, or I will call it f strict, as from m to n by, well, first you change your class by Tom class. Well, here I didn't say it, maybe that, well, yeah, I need f to satisfy some things. I need this bundle to be spin C. Okay, so this is what it's called K-oriented. And then, well, this is the cotangent and well, the dual, and then you move to the tangent part by some Fourier isomorphism. So it's just an algebra. This f comes from some isomorphisms of algebras. It's the Pond-White Fourier isomorphism. And then this is where the interesting part comes. So the evaluation at 0 becomes an isomorphism. And then you go to the differential, to the K-theory of df, so the deformation object. And then you just evaluate it at 1, and then you get here. But we are talking about groupoids. So in my notation, the K-theory means the K-theory of groupoids. So for example, here is very important because it's not just m times m, but it's the C-star algebra. So it's in fact the compact operators tensor the algebra of n. And then you have a Morita, an isomorphism induced by Morita equivalence. And this is f strict. It can be shown to be exactly the family index in the case where the family index makes sense. In all cases, we know. So, okay, so this was not equivariant, but how to pass to equivariant.
Sorry, may I have a question?
Yeah, sure.
So in the previous slide, E1 star is also an ISO, or
no,
not?
It's not. And in fact, it's the only one. All the others are isomorphisms, except for the evaluation at 1 in general.
Except all this. Okay,
yeah.
Thanks.
So in fact, yeah, this is very interesting because at the end, the other ones are very natural cohomological. Well, this one is just coming from an isomorphism of algebras. This one is in cohomology is very natural, and this one as well is just a very, even in this direction, is very simple to compute. So at the end is how to.
We don't assume anything, any relation between M and N, so
No.
there shouldn't be an isomorphism between K-theory. Yes, yes, sure.
But in fact, it's a nice comment because this you reduce your problems to compute everything in a devolution at one. This is, I think, one of the main main features of this tangent groupoid approach and deformation of groupoids. Yeah. So in the equivariant case, well, in fact, the functoriality of the deformation to the normal cone allows you to have an action. So if you have an action, so if gamma acts on a manifold A and preserves a submanifold B, then it acts on the deformation. And this is what I'm implying here, because this is again just the observation that deformation to the normal cone was functorial. Here, in fact, this is applied to a groupoid. In fact, this gamma is a group, is a discrete group in all the talk, countable discrete group for some reasons that I will mention after. And by functoriality, this is just a very trivial consequence of the functoriality again, is that it acts on the deformation, and then you can consider the semi-direct product groupoid associated to the action. And then the push forward follows the same things, because now, well, we dispose here, this is proper, maybe I didn't say it, but now I will assume M is it's a gamma proper manifold, and this has a gamma spin-C structure. And then you can, in these cases, you have Tom isomorphism, as perhaps first done by Kasparov, but in the sense of groupoids, maybe also by Pierre-Yves Legal, and well, this is in proper cases more or less classic. Then the other maps are the same the same point-wise. For example, here again you have an isomorphism of algebras, inducing an isomorphism in K-theory, and the other ones is the same. This is more or less classic in nowadays in index theory using deformation groupoids, how to define these maps. But well, my point is that here I'm using just groupoids and some cohomological properties as Tom isomorphisms, homotop invariance, existence of 6-term exact sequences, and so on. And well, these properties are not just exclusive of K-theory, because we have also heard a lot during the week. There's of course a very close relation between K-theory and cyclic cohomology, and in particular cyclic periodic cohomology. In this case, if you have the right algebras, then satisfies the properties as well. So homotop invariance in a nice setting, the existence of 6-term exact sequence, and well, it's natural, and the Morita invariance, I will say in some minutes. But just let me say a word of how to prove the functoriality, because this is just F strict, but how to prove the functoriality. So I will just to give you a diagram, because I think the diagram is very nice. So here you have a F strict, and here you have G strict. Define it by definition. This diagram is commutative by some kind of Tom isomorphism, and then deformation. Here in my diagram, I'm not putting K-theory and sister algebra, just putting the groupoids because of lack of space. But it also works for my point, because my point is that once you have the right groupoids and eventually the right algebras, then you can apply this construction for other theories than K-theory. So okay, so just if you want to prove the functoriality, well, you have to prove this, right? This is one-way functoriality. But now so you have to prove the diagram of the commutative of this fish diagram. And then here, in fact, with Biling, we use in K-theory, we use the idea that, well, at least I saw for the first time in a paper by Hilson and Skandalis about ground-wave functoriality. That is, the idea is of double deforming. So DF is these maps are constructing by deformations over the closed interval 0, 1. But in fact, what you need is to be able to construct deformations over a square. So here, what you need is something that deforms in the direction of f and the direction of g. So you should take double deformations. And this is also where the functoriality of the deformation of the normal cone is essential. But once you get it, in fact, then the proof, well, here I won't do the proof, but my point is that it's a geometric proof. It's you need the right groupoids. And well, in K-theory, because the properties were more established, it was more or less easy, but no. Okay, so that's a wrong-way functoriality. And well, okay, my point is that I will use these properties for similar constructions in periodic cyclic cohomology and in more geometric cohomological theories. For example, because I want to go now to a little bit to geometry.
Sorry, may I have a question?
Yeah.
So on this big diagram, the map little m is in fact not a map, yes, but it's well defined on the level of K-theory, yes? Is it right?
Yes, in fact, well, in fact, it is a map in, well, the projection to a point, in fact, is the Morita equivalence of groupoids. It's just a coincidence. But in fact, in my diagram, it's just sketchy. So in fact, this diagram should be in K-theory. So it's induced map, is a map induced by the Morita equivalences of the corresponding sister algebras.
On the level of on the level of K-theory. Okay, thank you.
Exactly. But it's good that you ask this because it's also a Morita. I mean, there is in fact a groupoid morphism that goes in that direction. That is an isomorphism of in this category of differentiable stacks. The inverse is not a map; it's a generalized morphism. For example, in the sense of Hilson's Candalis. So it's an honest map that depends in which category. But in the category of differentiable stacks, there is an inverse.
I see. So this is a genuine projection, yes?
Yes, exactly. In that direction, yes.
Thank you.
So now, well, I mean, the idea is to adapt this to cohomology to be able to give a Chern character and eventually then a formula. So sorry, I will speed up. So here is just a model for this is just by definition, but I would call it like that in this talk. So is the cohomology with compact supports over this action groupoid. So there's for groupoids there's the RAM model of cohomology and cohomology with compact supports using a natural bicomplex associated to this Lie groupoid. So this you can see it, for example, in a Brand. Brand has a very nice survey, but he writes a lot of details on this with the Brand and Ginot and Chou in an asterisk paper in the string topology, I guess, but they do it for Lie groupoids. Okay, so these groups are good for Chern characters because well, there is an isomorphism, once tensoring with C at least, with the K-theory of the proper actions, and this well passes by the Chern character, and then some explicit morphisms, which I will call here the Tushu isomorphisms, even if perhaps there are other kind of computations of this for this particular case. Tushu, they did it for more general case, but in fact, for us, their model was very appropriate. Okay, so in fact, yes, maybe I will try to get fast in at least one part. So the point is to be able to define push-forward maps for these delocalized objects, which again, I repeat, this is via the Chern isomorphisms, isomorphic to the K-theory that we assembled to form the left-hand side of Baum-Connes, at least in this model. So the delocalized, the Schurk map in this model is essentially follow the same lines. You take a Thom isomorphism, which exists in this proper action case. It's a very geometric thing. And then you go to algebras by using these two Chou isomorphisms. And well, there's a very technique point, but it's important is to do, you have to allow now for what it will follow, not just compactly supported function, but Schwartz in some directions. So these are not really Schwartz functions, but just Schwartz in the directions of the vector bundle fibers. In the other directions is compact support. So, okay, so once you do that, you essentially have the same definition as in K-theory. So in particular, there is a deformation map. This is so that there is an isomorphism induced by devolution at zero by some in fact in my thesis some years ago with George Skandalis, I defined this kind of algebras that gives the deformation between the Schwartz algebras in the tangent parts and the compactly supported part at one. So this is, we call it Schwartz type algebras. They are not again Schwartz. So they are Schwartz in some directions. But in fact, this was improved later by the board and the Skandalis. In my thesis, I just did it by hand. These algebras, they exist. The main feature is to be able to have a family of algebras precisely that this one is devolution at one and this one is devolution at zero. So, and then, well, you have the Morita invariance also in periodic cyclic homology. This was shown for Lie groupoids by Perrault by giving a very explicit map. And the two-shoe isomorphism. So the map is the same. Well, not the same, but it follows the same ideas with the appropriate algebras. Of course, this is essential to have appropriate algebras. In particular, the choice of Schwartz allows to have a good control on the kernel of the deformation, and then to apply the contractibility and the homotopy invariance argument. And one of the main theorems that we have already posted in the archive some months ago is that this is compatible. You have this kind of commutativity diagrams with the shrinking K-theory. So this is the delocalized version of Riemann-Roch. I will say what delocalized. As some of you know, well, you need to put some things in order to these diagrams to commute some top classes, and this will appear in a very sketchy slide in which I will try to tell you how to prove this kind of diagrams. Well, once you have the right groupoids, again, deformation groupoids, the idea is, well, this is by definition commutative, is to decompose the entire diagram using the definition. So the first one is Tom, and then this is where you have to put thought classes precisely to have this commutativity. Then a big part of the diagram is trivial because the Chern-Baum-Connes character is natural with respect to morphisms of algebras, to morphisms induced by morphisms of algebras. And then, well, the Morita invariance, which is more or less classic. And the other ones are this is just by definition, and this is by definition. So this is just an idea of how to use deformation groupoids to prove this kind of index problems. Then, well, another thing I wanted to say that this is where I think my last talk finished in April. No, not yet, sorry. The one-way functoriality of this construction, that well follows the same lines as the K-theory proof. Well, it's set like that, it sounds easy, but well, you need the good groupoids, and you need to check that these good groupoids still work once you have the appropriate algebras. This is what we did now with Hang Wang as well. But the push-forward functoriality is essentially, it gives a lot of things. And in this particular case, it allows first to assemble all the push-forwards in a single group, which I will call here the topological cohomology of gamma, which is in fact will be delocalized. And because of the Riemann-Roch theorems I was announcing before, in fact, this is just a corollary, but it's in fact a theorem. But it's to resume all the results above. There is a explicit Chern character, because the push-forward functoriality commute with the ones in K-theory with the ones in cohomology once you put these classes. Okay, so here, well, you can say, well, maybe how to obtain formulas, because Okay, this is important. This is by Tu and Shu. This is just it's a Chern character, which is an isomorphism once you tensor with C. And okay, so what about the computation of this? You can go further. Well, yes, because the model here is very geometric, so it should be a way to compute. In fact, just to mention, in the paper in the archive, we mentioned the existence of a map here that I would call a mu, cohomological mu, to here. This map is true. You can see it in the paper on the archive. Now I will give a different description of this map that will allow to give a formula. Eventually, we can discuss if these two maps agree. But for the moment, I will give you another description, which is more of geometric nature. Because these groups can be, in fact, well, first, there's a very geometric construction, which is the integration along the fibers. So here I will tell you how to construct a morphism, which is I call Schrick, because in fact is really a definite associated to the projection 2 point, but it will give to a form group homology class here. Here by definition I will put this as a definition. Mattei has a very good discussion on using the Shapiro's lemma of how these groups in the right are in fact the groups on the left, which allow another definition by just the classic group of homology with coefficients in the model, the complex vector space generated by the finite order elements. As for example was talked in the last talk. It was exposed there. Here in my notation, gamma G is the centralizer. So I think I'm using Matsut's notation in his book. I don't know, but yeah, so this is not this is just notation. This is the centralizer of G. This is the finite conjugacy classes set. The classes the conjugacy classes of finite order elements. Sorry, and you choose one element by class, and then once you fix that, you define it, and this does not depend on this choice. And the definition is very geometric, because the group on the left is in fact defined by a bicomplex in the RAM cohomology, and in this group you can compute the RAM bicomplex very easily. You have forms of this type. Here, sorry, n is important. Here, n is the dimension of M. And then you just integrate along the fiber. So it's very geometric. I mean, of course, this well, now you have to prove that this, in fact, indeed it's well defined in cohomology. So, but it's quite classic, I would say, because you compare the first one of the lines in the bicomplex defining this to the complex that defines. Sorry, here I put it just for M and gamma, but it should be done for every G. But the idea is that you take a form and you just integrate it along the fibers. And then one of the things we did since April is to prove that this is well defined. So this passes to the group of the assembled group. So in fact, it's compatible with the functoriality. This is not trivial, because now you have to show that you have a diagram, a compatible diagram between these Schricks. But the Schrick here is defined using cyclic periodic cohomology, and the other ones are using just integration along the fibers. So it's not trivial to prove it. In fact, I have to thank the referee of the first version of the paper that pushes to complete the program, because and in particular he mentioned a paper by Mattei that was key for what it follows, and it's really a very interesting paper. And now I will try to finish in the next just 5 minutes to describe how to prove that this is true. Well, you can just try to prove it by hand, but I found it very hard. In fact, I don't know still how to do it directly using cyclic periodic cohomology. But okay, so I will give you the strategy of the proof. So you want to prove that this map is well defined. But well, you could say, well, you have this Chern top character, so you can say, well, maybe if I prove that from here is well defined, then this one is well defined because this is an isomorphism. But still, this is not very, is in fact as difficult as the other one. You can say, well, in fact, this is where we complete part of the program that was not in, is not yet in the archive. This part is that, in fact, using Poincare duality against Schrick comparison, we can show that, in fact, our model is indeed the same model as the equivalent K-homology of the proper the space that classifies the proper actions. In fact, here we use, in fact, in a very strong way, the previous work of Baum, Hickson, Schick, in which they compare the Baum-Douglas model with this analytic model. So once the push forward is defined, and once you have the functoriality, in fact, is essentially what they did. But you need to define this group first. So once, okay, you can say, well, maybe I proved that this is well defined. Well, it still is harder, because usually the inverses of these lambdas are extremely complicated. You have a K-homological class, and then you need a cycle. Is very hard. But in fact, this is where Matei's work comes. And I have to say that this Matei has did it using a previous work of Luke, in which they localize the Baum-Connes assembly map, because here you have Baum-Connes, at least tensor it. By well, he defined an explicit isomorphism. Here is the K-homology of the space B gammas, of B gamma G. This is just for finite order elements. Okay, this is just that, because we are talking about proper actions. And in fact, the strategy of our proof is essentially to prove that from here is well defined. But still, it was hard because you need geometric cycles. And in our definition, we use geometric cycles, and path to B gamma is not so explicit. So in fact, what we did is to complete this kind of diagrams, because you can define actually the same group as I did before, but you just by allowing free actions. You just take cycles which are free and proper. And in fact, our strategy was to show that this will be posted very soon in the archive. That in fact, this is well defined, because somehow using that Matei's group, isomorphism is very explicit. One can prove that this map is well defined by somehow restricting this map to free and proper cycles, which are then more easy to handle. Because in the free proper case, this group point is Morita equivalent to just the quotient, because the quotient admits a good C-infinity structure. So well, once it's well defined, then well, you can use this is of course a very nice. I will just state the theorem. The last theorem is that you can compose the morphism. Sorry, let me recall you what the morphism was. So the idea was to define this integration along the fibers to get a more cohomological assembly map, and then the idea is to go to cyclic periodic cohomology. And this is was discussed in several talks. The previous one, for example, there is a by the work of Burgalea. There should be a nice. This is only for describing the next theorem, because once we have the assembly map in group homology, one can already have a pairing formula. But okay, you take Burgalea's map and you compose the Burgalea's map. So this map has as image just the part that depends on the finite order elements. And then, okay, so this was also recalled, I think, in the last talk at least, I don't remember, but the cyclic cohomology, this time cohomology, also was computed by Burgalea and other authors, and it has a finite order factor and another factor that depends on the infinite order elements. This won't appear in the pairing in our formula, because the map already has image in this part of finite order. And just for finish, well, notice that to the natural projection of groupoids, there is in cohomology a pullback map. This, in terms of BG, is just, for example, when the action is free, this is just this, and then you take the pullback when the action is free. But when the action is not free, you need another model for this. And okay, so this is essentially, I put it here because it's dual to the integration along the fibers. It has to be proven, but it's true. And then you have the final theorem, which tells you that, well, if you take the composition of this Chern character together with the assembly map I just described, then this induces a well-defined pairing from the left-hand side of Baum-Connes with cyclic periodic cohomology, and well, you get the formula, because this map is by definition just well, essentially up to Burger-Lea's computation is just Chern, Todd, and then is given in the G component is given like that for G of finite order elements, and then you have to go to cyclic homology using Burger-Lea's computation. So that's it. And this morphism, we call it just the Chern-Baum-Connes assembly map. I found this better as a good name. And well, this is this formula is just between this right hand side is really a pairing between forms and currents. And I think all the known formulas the formulas we know are exactly like that. It is. And well, I thank you very much for your attention. Sorry, it was very speedy at the end. So, well, thank you very much. Sorry.
Thank you, Paolo. Very interesting talk. Do we have a question?